Here's an interesting question, or at least it leads to some pretty interesting questions. Is a collection of logical operators, also known as sentential connectives, functionally complete? What does functionally complete even mean? Now, before we attempt a more formal definition, I think it's best to jump into some concrete material. That will make things a lot simpler. Generally speaking, we tend to think of 5 main sentential connectives or logical operators in propositional logic, namely the not, the and, the or, the conditional if-then, and the biconditional if and only if. We can ask the question, do those form a functionally complete propositional logic? And one way we can answer that is as follows. Let's say we have the atomic sentence P, we have the atomic sentence Q. We can construct some truth tables, and in fact, I've already done so. For example, we can say that P is true, Q is true, P is true, Q is false, P is false, Q is true, P is false, Q is false. And I, so to speak, repeat that pattern. So for P, we have the pattern true, true, false, false. And for Q, we have the pattern true, false, true, false. Now also notice I have all these different possibilities in terms of the outcome, or the outputs, given those inputs. For example, we might get the output of all true values. We might get the output of all false values. We might get the output of this, false, true, given, so to speak, these inputs. Now, in fact, there are 16 possibilities in terms of all possible outcomes. And that's because in the first row, there are only 2 possible outcomes, either true or false. But likewise for the next row, and likewise for the next row, and likewise for the next row. Thus, we have 2 raised to the 4th power of possibilities, which is just 16 possibilities. And so, we will have a functionally complete set of logical operators if we can form a molecular proposition for each and every one of those possibilities. In other words, we should be able to form a molecular proposition, also known as a compound proposition, composed of at least one of those atomic sentences and of at least one of those sentential connectives, such that we get all 16 results. For example, there should be some proposition that will give us all true values. There should be some proposition that will give us all false values, or some proposition to get the values false, true, false, true. Likewise, there should be some proposition to get this result, true, true, false, false, and so forth. And if we can do that, we've exhaustively proved that we have a functionally complete set of logical operators or sentential connectives. And by the way, this is a good exercise. Can you get a proposition? Can you figure out some proposition to get each and every one of those results? You might want to pause the video and try that yourself. Now, in a moment or two, I'll show you what I got. So let me do that right now. And your results might look a little bit different, and that's not necessarily a bad thing because, strictly speaking, there are infinitely many possibilities. So for example, to get this result, this tautology of all true values, we can form the molecular proposition P if and only if P. To form this, all false values, we can get not, parentheses, P if and only if P, close parentheses. To get, for example, this, true, false, 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 we can compose a molecular proposition P and Q, and so forth. So this exhaustively shows that the not, and, or, if then, if and only if are functionally complete. Now perhaps we can say then a more formal definition of what it means to be functionally complete is to say that we have a set of logical connectives or logical sentential connectives that is functionally complete if and only if for every Boolean expression, and a Boolean expression just means we have an expression that's either true or false, is equivalent to one involving only these connectives. And we have shown this because each and every possibility here, we can form a molecular proposition with these sentential connectives. So it's functionally complete. Perhaps a more interesting question is the following. Are there redundancies, so to speak? Do we, strictly speaking, need all 5 sentential connectives to have a functionally complete set of logical operators? But if you think about the logical equivalencies, in fact, it must be the case that there are, so to speak, redundancies. For example, consider the conditional, if P, then Q. In propositional logic, that's logically equivalent to not P or Q. And so, we can re-express any conditional in terms of negations and disjunctions. Moreover, note that P, if and only if Q, is logically equivalent to if P then Q and if Q then P. But that's just logically equivalent to not P or Q and not Q or P. And thus we can re-express any biconditional in terms of negations, disjunctions, and conjunctions. But this shows that we have informally proved that the not, and or is also functionally complete. And that's kind of interesting, I think. The conditional, strictly speaking, is redundant. It's not necessary. The biconditional, strictly speaking, is redundant. It's not necessary. They're useful. They're very useful. But they're not strictly necessary in order to work with propositional logic. But could we have only 2 sentential connectives and still have something that's functionally complete? Well, think of De Morgan's rule, De Morgan's law. Let's say we have P and Q. But that would logically be equivalent to not parentheses P and Q by double negation. And that would be logically equivalent to not parentheses not P or not Q by De Morgan. And so it follows that the not and the or is also functionally complete. And we have informally, one might say, proved this. Any conjunction can be rewritten using negations and disjunctions. But likewise, not and, that's functionally complete. And we can show that using the same kind of logic, so to speak. So let's say we have P or Q, but that's just logically equivalent to not parentheses P or Q. That's logically equivalent to not parentheses not P and not Q, close parentheses. So any disjunction can be rewritten with negations and conjunctions. Now, by the way, could we have the not and the if then? Would that be functionally complete? How would we show that? Well, we would have to show that P and Q could be rewritten in an equivalent manner that only uses the negation and the if then. Likewise for the P or Q, and likewise for the P if and only if Q. And that's a good exercise. You might want to try that yourself and pause the video. So for the conjunction, we could actually rewrite that the following way. So not parentheses P arrow not Q. For the disjunction P or Q, that's equivalent to, in propositional logic, parentheses P arrow Q, close parentheses, arrow Q. And the biconditional P if and only if Q is logically equivalent to not bracket parentheses P arrow Q, close parentheses, arrow not parentheses Q arrow P, close parentheses, close brackets. Now we can prove that, for example, with the truth table. But we also could derive that using our various rules of inference or logical equivalencies, just as we went from this disjunction to this to derive finally that. So you can do some kind of process just like that. Now finally, could we have only one sentential connective that's functionally complete? I think you should suspect that in terms of our 5 main or common sentential connective, that's impossible. We need at least 2. We need the negation and some other sentential connective. However, there are 2 less common sentential connectives that in fact are functionally complete. So on the one hand, you have the so-called NAND, N-A-N-D. We can represent that with a downward arrow. We also have, that's the NOR. So the NAND is with an upward arrow. That, in fact, is functionally complete, interestingly enough. We also have the NOR, N-O-R, and that's represented with a downward arrow. And that by itself actually is functionally complete. But perhaps proving that is for another video. What I can say here is just that the NAND is the complement of a conjunction. In other words, it has the exact opposite truth values of a conjunction. And the NOR is the complement of the disjunction, that is to say, the inclusive OR. So it has the exact opposite truth values of a disjunction. But the NAND is functionally complete. You can represent any proposition in propositional logic just with the NAND. And likewise for the NOR. At any rate, I think the initial question actually did raise some interesting questions. For example, how many sentential connectives do you really need to have a functionally complete propositional logic? Regardless, I do hope this video has been useful and helpful to you. I hope you learned something. If you did, please consider visiting my website at amateurlogician.com, and I'm going to construct many more of these videos in the future. Thanks.